All right. Let me begin with a word of prayer. So I'll start. Dear Father, we thank you for this day. Again, I thank you for this class and this time we have to meet and study your creation. Just pray that you be glorified we do, and that you'd help us to all understand differential equations a little bit better, Lord. In your name I pray, Lord Jesus. Amen. All right, so I told you guys last time, to solve the first order differential equation, we got basically four methods: separation of variables, integrating factor method, exact equations, and then substitutions. All right, so substitutions is where we'll be sort of more focused today. But I'm going to start by sharing with you guys a kind of neat little theorem that allows us to solve exact equations in a kind of neat way. So let me write down the theorem and then we'll prove it. So this is from page 23 of my notes. This is proposition 2.3.7. So suppose we've got m dx plus n dy is equal to 0. Suppose that is exact on a simply connected region U, which is a subset of like R2, okay? And so for us, that's just going to mean at the moment that it satisfies the closed condition. Like, I'll explain better next week why this is a reasonable thing to say, but we have, let me just say it this way, we assume that partial m partial y is equal to partial n partial x on U, all right? Then the solution through x naught y naught in U is given implicitly by following formula: the integral from x naught to x of m of t comma y dt plus the integral from y naught to y of n of x naught comma t dt is equal to 0. All right, so this is the claim. And so this is kind of neat because it gives you a stone cold formula to like solve a differential equation. So you guys, you'll choose your adventure. Show of hands, who wants to see proof of the proposition first? Who wants to see an example with the proposition first? Examples have it. All right, so I'll start with an example. Suppose you've got we've got 2xy plus e to the y dx plus parentheses 2y plus x squared plus e to the y dy. And we want to find solution through, oops, let me write over here. Find solution through the origin. All right. So first of all, let's just double check here. Is this an exact equation? In the sense, does it check the so-called closed? So this guy's up here. This has a name. This is the so-called closed condition. If the closed condition holds on a simply connected domain, that suffices to make it an exact equation. All right. Now, So is this an exact equation? I mean, does it satisfy the closed condition more precisely? If this is m, and this is n, is it the case that, m sub y, which is the partial with respect to y, so that's what? That's 2x plus e to the y. Is that equal to n sub x? Is that equal to the partial derivative with respect to x of the n? I got 2x. Yeah, good. So this satisfies the closed conditions. So for theoretical reasons that I will blather on at length about next class, that makes it an exact equation. All right, so since you guys chose this, we're going to use the formula blindly, trusting my past self who wrote these notes. All right, so we're supposed to do the integral from 0 to x. Now this right here is m of x comma y, right? And this is n of x comma y. So we've got to do a little evaluation here. What is m of t comma y? If I plug a t in here for x, what do I get? I get a 2 ty plus e to the y dt in the formula, right? In the formula. Plus what? Plus the integral from 0 to y of n of x naught t. Yep.
I could be wrong, but aren't the possibilities not equal to each other?
No, they're equal. So next one here. What?
But the e to the y, wasn't it if you take partial derivative with respect to x on the n? Isn't it e to the y?
Oh man. Oh no. Well, this is unfortunate. Let's see here. How can we fix this? So what do I need to do to the n in order to fix this example? Put an x on e to the y. Right, let's fix it. So if we put an x right about here. Thank you for sticking to your guns. Very good. If you see something, say something. That seems to be my theme for this week. So I think if we do that, we're good, right? Because then the partial derivative with respect to x it gets me an e to the y and the 2x. 2x plus. Yeah. All right, so far so good. That didn't affect what I already wrote in purple, so that's good. Thank you. Perfect timing. 3 minutes from now, that would have been really annoying. So thank you. Thank you, thank you. Now we're supposed to calculate n of, to put down here, we need to look at like n of what? X naught is 0 for this. We need to figure out what n of 0t is and put that here. So my x is 0. Oh, hey, that's nice, because then my y is t, right? So I got 2t, and my x is 0, so it's just 2t, 2t dt. Yeah. Well, I need to correct the notes. That's good. This, of course, has been pointed out to me many, many times because all of the students work through my notes carefully. The dozen times I've offered this course since I wrote these notes. Hundreds of engineers. Never a question. That's not on you guys. You guys fixed it, right? I need to go back and like change some grades or something. I don't know. I can do that, you know? Okay, I'm just joking. I'm too busy. Okay, so I don't think I have the power to change grades retroactively. I've never tried. So we can do these integrals, right? What do we got? The integral with respect to t, the y is a constant here, right? So this just integrates to t squared y. And this guy integrates to plus t e to the y. I got to take that fundamental theorem of calculus and evaluate from 0 to x, right? This one integrates to what? T squared. And again, I have to evaluate from 0 to y in this one. The other one from 0 to x. Okay, so do the math. That gives me x squared y. plus x e to the y. Now when I plug in t equals to 0 here, right? Maybe in this kind of thing, when there's so many letters flying around, it's not the worst thing in the world to use a little bit of extra notation to indicate what you're doing. So like here I mean t equals to x, right? I mean t equals to 0. That's what's going on here. I'm doing an evaluation in t. Yeah? Just so we're clear. Anyway, so I've got x squared y plus x e to the y. When I plug in t equal to 0, nothing, right? And then the other one, what do I get? Plus y squared, yeah. So supposedly, this equals to 0 is my implicit solution that goes through the point 0, 0. Now, does that go through the point 0, 0? Plug in 0 and 0. Did you get 0? Yep. So it's definitely going through the origin. And the other thing we should do to check on this is if we take the total differential of this, right? Remember calculus 3, you learned to take the differential of a function of two variables? Do that. If doing that gets you back to the differential equation, we did it right. So if we take the total differential of this, what do we get? So partial differentiation with respect to x. So what I'm thinking of is this thing is f. Let me write down the pattern. So I'm doing partial f partial x dx plus partial f partial y dy. That's the total differential. For this particular choice of f, that gives me what? That gives me 2xy plus e to the y dx plus partial x squared plus x e to the y plus 2y dy, right? What is that? Go back to the differential equation which was given, right? I'm sorry, guys, my bad. What did I forget here? Kind of an important thing. Is this a differential equation? It's not an equation without an equal sign, right? So we probably we'd afford to add a 0 here. 0 equals to that, if you'll allow me that short manga style calculation there. Comment. So 0 equal to this. Well, this is that, and this is that. So indeed, the boxed equation in black has this differential equation as a differential consequence. That is to say that this differential equation has this as a solution. And which solution is it? It's the one that goes through the origin. So I don't think this particular formula is in Nagel, Saff, and Snyder. I found this in a book by Ritger and Rose, which is a very popular differential equations for your grandparents. But it's a good book. It's also available in Dover for about $5. So I've used it for the book in this course before. It's a nice book. Okay, so let's look at the proof for this formula. Let's see why this works in general. I'll try to be brief because that's not really what we're terribly interested in. But what happens when we, let's see here. So let me call this whole thing right here. Let me call this f, all right? So let us consider partial f, partial x, right? What's that equal to? It's partial x of the integral from x naught to x of m of t comma y dt plus the integral from y naught to y of n of x naught t dt, all right? So I need to calculate the partial derivatives. And if I can show that these partial derivatives are m and n respectively at xy, that will prove that that is the solution to m dx plus n dy equals to 0, right? If I can show that the general formula has as its differential consequence m dx plus n dy equals to 0, yeah. Okay, so how do you do that partial derivative? What goes on here? What happens when you differentiate a variable bound? It cancels. And what happens? You take the integrand and you evaluate it at the bound, right? So that is to say that this first term here is just going to give us m of x comma y. All right? That's just this piece. Now what happens when we partially differentiate with respect to x on the other piece? Well, there, I got to do a little sleight of hand, guys. So this is an abuse, but it's an abuse that I make in pretty much every, 300 level, not really pure analysis class, a class where we do calculus, but we do it in a slightly slovenly way. Now, it may not feel like that to you, but there is an abuse there, because I've brought the derivative inside the integral. All right. This is possible provided that the function n isn't too misbehaving. All right. But it turns out in this context we can assume that, so this is a reasonable step. Now, so I brought the derivative inside the integral. All right. Notice this is differentiation with respect to x. That was integration with respect to t. So there's nothing. And then what? Oh, well, look at this. We've got partial n partial x, right? What is that equal to? Remember, this is also equal to partial m partial y at x naught comma t dt, right? I'm using the assumption of the closed condition to switch the partial derivative with respect to x to a partial derivative with respect to y of the other function. That's where you stop for this part. This is a meet in the middle kind of proof. So if we do partial f partial y, what do we get? Oh man, I'm sorry, I stopped too soon. Whoa. Oh, I'm an idiot. Wait a minute. Oh man, I'm organizing the calculation on the board in a totally different way than in the notes. Phooey. Tell you what, I think the best thing to do here to put us out of our misery is for me to use the projector for a minute and just show you the proof from the notes, because like that's going to be a better use of our time, I think. So, also, it will give me a chance to give you the ever exciting and anticipated, you know it, you love it, Top Hat code. I know you guys all want to be joiners, right? See here. So sorry about that. I mean, the calculation I was doing is fine. It's just not going to get to the point, and I don't really want to spend a half hour doing this proof today. So like, let's not do that. You guys want to see me do examples, not proofs, I think. Usually. There are things in here we need to prove, because if we don't do the proofs, you don't really understand, the structure. So the join code is 369137. Again, I do take attendance with the paper, not with this so much, yeah? All right. All right, let's see if I can find. Thank you, sir. Anybody remember the code?
The join code.
Whoa, we're in the future. Way in the future.
Yeah.
What's the code? 5918. All right, guys, I will eventually get back to where we were. Come on. You can do it. Oh, man. Here it is. So, this is page 23. So this example 2.3.8 is the one that Addison? Is that right? Addison? And what's your name? Ashton. What's wrong with me? I know your last name, but anyway, thank you for noticing that. Okay, so here I take the partial derivative. I take the total differential of the m formula, m part of the formula, and so it's the step that I just made, right? So I have partial derivative with respect to x plus the partial derivative with respect to y with the differential. That's the total differential, right? This piece just gives us back that, like we were just talking about. But this piece we didn't do. Partial derivative with respect to y. I bring the partial derivative with respect to y inside. Then I use the closed condition. That converts this to an x derivative, which is super nice because then you've got integration of a total derivative, which then just gives you the difference in the thing being differentiated, namely n of x comma y, and then minus n of x not y not. Now that's got a dx, that's got a dy. So that's half of the differential. The other half of the differential comes from differentiating the other part of the formula. So I take the total differential of that as well. And when I do that, I've got the x and the y derivative. Now, this right here, what's the partial derivative of this? Do you see any x dependence here? So this is 0. And then over here, again, they cancel out, so to speak, right? Fundamental theorem of calculus part 1, and that just gives us this. But that is exactly the thing we wanted to get rid of from the total differential of the other piece. So lo and behold, we have m dx plus n dy is the differential of this integral formula. So this is kind of a slick formula you can just use to straight calculate the solution to an exact equation if you want. I don't always use this. In fact, I tend to forget it, but I think it's fun to look at. And like here's an actually correct example with it. Another one, if I have like 2dx plus 2dy equal to 0 through x naught y naught, the formula gives me this, which pops out x squared plus y squared equals to x naught squared plus y naught squared. The cool thing about this formula and method is it automatically fits the curve to the point that you're interested in. And it can produce formulas that will fit a curve through an arbitrary point, which is kind of neat, right? Our other method was to do this integration of the equation, and then afterwards we'd have to fit the constant to get the point, So this is a nice thing to know about. But anyway, yeah, questions? Let me put this away then. I have other things to show you today. Yeah.
So you could use this for like the values.
Well, the place to use this would be, yeah, if you have a initial value problem and your problem happens to be an exact equation, it's a nice method. Of course, there are some dangers here. The reason I don't teach, you're like, well, why don't you just teach this as the way to do it? Well, because the whole evaluation at T business in here is a place where students are going to make mistakes. And so, like, a lot of people are going to get a wrong answer from this because of not carrying out this formula correctly. I just think it's probably better for you guys not to do this, honestly. You're like, well, why'd you do it? I don't know. I do what I do. Don't ask me these questions. Let's look at another one. So here's a definition. If m dx plus n dy equals to 0 is not exact, however, im dx plus in dy equals to 0 is exact, then I is an integrating factor for, let me give this thing a name, star. All right. So what would would this mean? What condition would I have to solve? What does this mean? You'd need what? We need that the partial derivative with respect to y of something equals the partial derivative with respect to x of something else. Fill in my blanks. What goes there? If im dx plus in dy is exact, what do we have to have? Small victories. I remember to move the camera back down. What's that? Oh, that's not going to work because this is not an exact equation, so those are not equal. What's that? I alone, that wouldn't do it either. What we want is im here and in here. That would make the new differential equation, let me call it star star, exact. Which means then we could solve it like an exact equation, right? Here's one. Example 2. So you guys, we've looked at this problem before. dy dx plus py equals to q, right? In fact, we already know how to solve this, don't we? Now let's understand what we're doing from a slightly different perspective. So here I'm assuming that p and q are just functions of x. Does that make sense? The way I wrote that, p is equal to p of x, q is equal to q of x. That I'm saying they're just functions of x. They're not functions of y. Okay, so let's write this in Pfaffian form. What's that? We've got, like, let's see here. Py minus q dx plus dy is equal to 0. All right? So I just rewrote it in Pfaffian form. I multiplied by dx and put everything on one side. All right, let's identify what's m and what's n here. This is my m, and my n is what? It's 1, right? Is this an exact equation? Does it satisfy the closed condition? No, I don't think so. Notice that like m sub y is p, which is not equal to, n sub x, right? Unless what? There is one case where this would be an exact equation. What is that case? P equal to what? What's that? What'd you say? 0, yes. Believe in yourself. You can do it. So, I mean, in here, if I ask a general question like that, it's almost always the answer is either 0 or 1 or whatever the letter is that we're looking at. Those are your 3 guesses. So yeah, this is not. So if P is non-zero, this is inexact, right? So it's inexact. So let's try. We want to have partial y of I times m, right, equal to partial x of I times n, right? So that we want, whatever we make our integrating factor, that's what it needs to solve, right? But here m is what? I mean, yeah, m is, so we've got I IPY minus IQ, right, is equal to partial x of just I guess, right, because n is 1. So in general, you could think about a lot of different ways to solve this. But an important idea in differential equations is to never make things more complicated than they need to be. All right? So like, if we can find a solution with a simple assumption that works, then let's go with it. So like a simple assumption here to make is to, like, let's try I is just a function of x. Just a function of x. Then we can do this calculation a little bit easier, right? This becomes what then? If I is just a function of x, when I take this partial derivative with respect to y, notice that IQ has no y dependence whatsoever. It's just a function of x. So this is just differentiates to 0, and we get IP is equal to partial I partial x. But if I is just a function of x, that's really the derivative, the total differential with respect to x, truth be told. So then, this gives us that di over I is equal to, well, p dx, which we can integrate both sides. We can separate variables, integrate, we get natural log, the absolute value of I, is equal to the integral of p dx. And that gives us that I is equal to, the absolute value of I is equal to the exponential of the integral of p dx. Lo and behold, this suggests that we should choose I as the exponential of the integral of p dx, which, good news, we were already doing that. Right? This is the integrating factor of the integrating factor method. This gives you some indication of why we make it what it is. Because what multiplying by that factor does is it takes your given linear differential equation, and if you rewrite it in Pfaffian form and multiply by that, you get an exact equation, which we can solve nicely. Right? So, which isn't to say that we use exact equations to solve the integrating factor method. I'm just saying it's behind the curtain, so to speak, of the method, yeah? All right, enough about that. Let's look at another one that's kind of more annoying. This is just motivational. So if I have demotivated you, my apologies. So here's example 3. Suppose you've got 3x plus 2 over y dx plus x squared over y dy equals to 0. Let's find an integrating factor to make the equation exact. Now, unless the problem is pretty simple, I almost always will give you guys some kind of hint about what to use for the integrating factor. So like here, what we're going to do is we're going to try I equals to, let's say, x to the a times y to the b, and see if that'll work. I mean, it's going to. Let's try multiplying by this. Where here a and b are powers that we don't know yet. Oh, I don't know. Can you guys tell me what to multiply by to make it exact? Maybe somebody can guess it without looking at their notes. I can't, probably. I don't know. Maybe if I tried both the first power, 3x squared. X squared. Yeah, well, I don't know. Let's work it out though. So what we do is we multiply by I, and we get x to the a, y to the b, times 3x plus 2 over y, dx plus, x to the a, y to the b, times x squared over y dy, right? Let me clean that up just a bit. So what we're looking at here is 3x to the a plus 1 y to the b plus 2x to the a y to the b minus 1 plus, that's dx, plus, let's see, over here I've got an x to the a plus 2 y to the b minus 1 dy. Right? Now we're doing it for arbitrary a and b to give ourselves the flexibility to find what's going to work, you know? So, okay, so what do I need then? So if I call this thing, you know, m, and if I call this thing n, what do we need? What we need is m sub y equals to n sub x, right? We need the y derivative of the dx coefficient to be equal to the x derivative of the dy coefficient. That's the closed condition that will give us exactness. Oh, I probably should move the camera. Sorry, people at home. Oh, I was about to tell you guys I plan to plan to lecture Monday, but that seems irrelevant to you. You know? So, enjoy your day off, I guess. Well, every Monday's a day off in this class, right?
Yeah. Is there no classes on Monday?
The classes are virtual.
Virtual?
Except I'm holding my virtual classes in class. So, you know, us math people are like that. We don't like taking days off. I mean, classes are not canceled, they're virtual. So what that means is 30% of the classes are canceled for the people who just are like, this is dumb, you know? And then the other 70% of us are like, I can't lose a day. I've got stuff to cover. My class is about something. I can't just skip a day. It's not fill in the blank or fill in the blank. I won't say the courses, but you know them. See here. So, see, that's a general, that's an abstract insult. It applies to every course you don't like, see? But I'm guilty of accusing no particular course of anything. It's really the most cowardly way to make insults. But it is the modern custom. Don't name names. Let's see here, sorry. Ever think about this? Not naming names is one of the most slanderous things. It claims to not be slanderous, but in effect it's slanderous because it puts the accusation on everyone you didn't intend. You know? By not naming names. So the partial derivative with respect to y brings down a b from the y to the b minus 1. And then I get plus 2 b minus 1 x to the a y to the b minus 2. So all I'm doing is differentiating n sub x. That's a little bit easier. That is 2 plus a x to the, I wish I had a bigger board, a plus 1 y to the b minus 1. Hey. Okay, so double check me. Did I partial differentiate correctly, I hope? Yes, no, maybe so. Okay. So, can this equation hold? What is it? How do you? We've got this guy right here, right? And we've got the same thing over here, don't we? So for this equation to work, we need 3b is equal to 2 plus a, don't we? Right? Use your imagination. I really want to write there. But I know, because somehow I know that if you write on this kind of like latex paint with a whiteboard marker, it's permanent. It's literally permanent. So there is technically a 0 times x to the a, y to the b minus 2 here, you know? I don't know if you can see it or not, but it's there. And so in order for these two to match up, we need that 2 times b minus 1 is equal to 0. So apparently, b is equal to 1. And if b is equal to 1, what's that make a?
1.
You say 1? Yeah, cool. Oh, you were right. Ah, hey, look at that. All of this calculation for nothing. We could have just multiplied by xy. You were right for once. That seems kind of harsh.
Oh, he says way neater.
Oh, he says, all right, well, I'll allow it. So multiply by xy, and we get what? We've got 3x squared y plus what? Plus 2x, the y's be canceling. And when I multiply x squared times y times this, I get an x cubed dy. Is that right? So what I did, guys, is I took the given differential equation and I simply just multiplied by the integrating factor that we determined will work, right? Do we agree? Yep.
On the right side of the board, how did you get the 3b equals 2 plus a?
Because the coefficient of, we have this power here and the same power here. In order for this equation to work, we have to have matching coefficients. You're used to it for one variable, but it's true for multinomials as well. If you have a multinomial in x and y, the only way for two multinomials in x and y to be equal is for all of their coefficients to match up. That is a result of multilinear algebra we will use. If you don't believe me, you could partial differentiate and evaluate at 0 until you derive this, whatever. But okay, so how can we solve this? I will tilt my head and squint and say that is the total differential of, well, x cubed y plus x squared, I think. So therefore, x cubed y plus x squared equals to a constant is the solution to star. Do you see what? Do you believe this? If I take the total differential of this, the x, partial x gives me 3x squared plus 2x. That's this piece. Partial y gives me x cubed. That's that piece. So the differential of this is that, which means that this, whatever this is, this level, this function, its level curves are the solution to that differential equation. This is almost true. There's one problem. This boxed solution here includes some things that are extraneous solutions, right? Solutions that we have adjoined to the solution set by multiplying by the integrating factor. Notice that this integrating factor is 0 when x and y are, when either x or y is 0, right? So if you're multiplying by something that's 0, you're destroying any information that was there before, right? So what that means is we should be very leery of x equal to 0 and y equal to 0. Notice that x equal to 0 and y equals to 0, I think are potential, you can find them in the solution set to this thing here, all right? But obviously y equals to 0 is not a legitimate solution here because it is outside the domain of the original differential equation, right? Because we can't divide by 0, yeah? So y equals to 0 is, in fact, a solution to this differential equation down here, right? It is. So y equal to 0 is a solution to the im dx plus in dy equals differential equation, but not the original one. I think x equals to 0 actually would be a solution. If you think about x being identically equal to 0, we get 0 and 0. I do believe x equals to 0 is not an extraneous solution. It's actually a legitimate solution to the original problem if you take a parametric viewpoint, right? If you're like the professor who used to work here and you insist that solutions have to be functions, well, x equal to 0 is not a function. But I don't think that's the right viewpoint because I don't think x and y are especially special. I think we should treat x and y on the same footing. So I don't think we should only think about functions of x. We should allow functions of y, right? And x equal to 0 is a perfectly good constant function of y. You can do that. Physics allows that. Engineering allows that. When you guys take thermodynamics, you have state variables. You can make any one a function of the other ones. There's nothing a priori that says everything has to be a function of energy. It might be a function of temperature. It might be a function of entropy. So what's a function of what? Well, that's a question of style, context. So I'd rather not prefer X and Y in my general story of how things work in here, you know? All right, let me go on. Substitutions, finally. I mean, this, I don't know, I guess this is technically special integrating factors. I don't require you guys to study section 2.5 in the textbook, which is on special integrating factors. It's not in my, if something's not in my notes, it's not on my radar pretty much, all right? So let us go on. So our next technique is substitutions. And there are basically, I mean, there's endless substitutions. There's as many substitutions as there are problems. There's all kinds of problems you'll encounter in a particular subfield or discipline where it has its own special substitution that's unique to the discussion there. Like if you take certain, like, I don't know, like physical chemistry classes, you might find there's a really special substitution to solve a particular decay rate equation, something like that. So I'm not talking about those. I will illustrate by example here. So one good example for us is simply this. If I can remember what example I'm on, that'd be lovely. Example 4. So here we have dy dx equal to x plus y minus 6 quantity squared. All right. So if it's something like this, what we're going to do is we're going to make a substitution. We're going to let v equal to x plus y minus 6. Because then we've got a v squared rather than an x plus y minus 6 squared. And v squared seems ever so much nicer, right? So you're like, that doesn't sound like an ironclad argument. Well, that's right. All of these things are educated guessing. And the proof is in the pudding, so to speak. If it works, it works. If you desire a higher standard of derivation, well, I welcome you to find it. So, all right, if that's the case, this is v squared, right? But what's dy dx? So what we need to do is we need to differentiate the substitution equation here. So this tells us that dv dx is what? 1 plus dy dx. So this is a lot like u substitution, where you have to substitute both the, the integrand and the measure. Similarly here, we have to substitute both parts of the differential equation, the part that's algebraic and also the part that's derivative. But as you can see, this gives us that what? Dy dx is dv dx minus 1. And as such, this becomes dv dx minus 1 is equal to v squared. This is a lovely differential equation because this takes us back to the start of things. This makes me nostalgic for the first 20 minutes of when I actually did math and wasn't just telling you words. Right? We can solve this with separation of variables. So this is dv over v squared plus 1 equal to dx. Integrate both sides. We know how to integrate, so we know that that's inverse tangent of v is equal to x plus a constant. As a general point of order, we'd like to find an explicit solution if we can. So this gives us v is equal to the tangent of x plus c. But what was v equal to? Oh, it was x plus y minus 6, right? So, lo and behold, this gives us y is equal to 6 minus x plus the tangent of x plus c. And that, my friends, is the explicit general solution to this problem. It's also a way easier problem than the last example, isn't it? I think. I don't know. In principle, the last one's easy, but this is a nice example. I like this example. So, like, general point of order, anytime you've got, some kind of differential equation where you've got some kind of like ax plus by plus c, if you got like dy dx equals to stuff, right, with something like ax plus by plus c, that pattern, maybe you can solve that with a v equals to ax plus by plus c substitution, right? Try that. That might be a good idea for that kind of problem, right? That's what we did here. Here's a different example. Example 5. Suppose we want to solve dy dx is equal to y over x plus 1 divided by y over x minus 1. Now, so in the practice problems that I've published for you guys, the way I come across a problem like this looks a little different. Let me try to show you like the source material for this example, if you will, because there's a different way that this one can sneak up on you. This is actually an example of what's known as a homogeneous differential equation. If I rewrite this in Pfaffian form, kind of show you the man behind the curtain here. So this is interchangeable. I'm not solving it right now. I'm just giving you a commentary, okay? So like y over x minus 1 dy is y over x plus 1 dx. If we multiply this by x, we get y minus x dy is equal to y plus x dx. Or if you like, we could write it as x plus y dx plus x minus y dy, okay? Like this is a homogeneous differential equation. Let me show you another one, just totally different. If you had something like x squared y plus y cubed dx plus the square root of x, square root of y, xy dy. I'm not going to try to solve this one, but that would also be like a homogeneous differential equation in the sense that like the sum of the powers of x and y, it's the same for each term. So like, see this one, like all of the powers are 1. This one, all of the powers are 3. 2 plus 1 is 3. 3, half a power, 1 power, 1 power, 1 half plus 1 half plus 1 plus 1 is 3. So this is also a quote-unquote homogeneous differential equation. So anything that looks like that, the technique I'm about to show you might work for it, all right? If you look at the practice problems in your homework problems, I give a slightly more general advice on how to solve these there. So, keep that in mind. But let's solve this problem, commentary aside. So what do you think we should let v equal to? I heard a y over x. I'll allow it. Now, do you want to differentiate y over x? No. So why don't we trade this out for a xv equals to y? That is ever so much more lovely. Differentiate that. What do you get? Well, you get yourself a v plus x dv dx is equal to dy dx. So that's nice because we can take that and put that up here, right? And so with this substitution, we got ourselves a v plus x dv dx equal to, well, apparently v plus 1 over v minus 1. It's a little scary looking, I guess. So what we probably should do is isolate the differential. So we've got x dv dx. This is good. This is going to give us a little review of some calculus we probably forgot. So we got minus v. What should we do now? So I just say, it looks to me like we probably can do separation of variables on this, but I probably need to clean up the formula for v before I do that. What should we do? Very good. So you are telling me to make a common denominator. And when I do that, what do I get? I get minus v squared. I get a plus v here. I get a plus v there, so I get a plus 2v. And I guess there's a 1, right? All right. I think I will do better if I factor a minus out. So that's a minus v squared minus 2v minus 1 divided by v minus 1. Which is all we need. So separate variables now. So what we get then is we get v minus 1 times dv divided by, let me absorb the minus into this. Well, I don't know. Fine, I'll leave the minus out here. I hate these, this minus is the bane of my existence here. V squared minus 2v minus 1. And that's equal to what? Integral of, let me put that over here. Integral of what? Yeah, so I put the dx over there. Yeah, dx over x. Thank you. Now this, I think if we just make that a w for the denominator, right? What's dw with respect to v? It's what? 2, like dw is what? It's 2v minus 2 dv, also known as 2 times v minus 1 dv, right? So this is literally, I keep the minus outside to try to keep myself honest. I get a 1/2 dw over dw, which gives me what? Natural log the absolute value of x. I'll put the constant over here because you got to put it somewhere. Equals to minus 1/2 is the natural log of the absolute value of w. But that is minus 1/2 the natural log of the absolute value. What was w?
V squared minus 2v minus 1.
V squared minus 2v minus 1, right? Which is minus 1/2 the natural log, the absolute value of y squared over x squared minus 2y over x minus 1. And that's equal to the natural log of the absolute value of x plus a constant. And there you go. That's an implicit general solution to this problem. So I